then I'll start going ahead and introduce today's speaker. So it's my great pleasure today to introduce Martin Centurion, who will be joining us from the University of Nebraska, Lincoln. And he's going to be talking about imaging ultrafast dynamics in molecules with electron diffraction. Back in the day when I first sort of started getting used to ultrafast spectroscopy measurements, then it was sort of very much the lore of the land that it was light to prepare the quantum state that you're interested in measuring and light to measure it. And Martin has been really one of the pioneers in sort of developing ultrafast electrons as a source of probing and using diffraction from molecules to understand what's going on. Martin got his bachelor's degree from the University of Michigan. And actually we overlapped, I just realized in looking up your CV during the time that I was doing my PhD there while you were an undergraduate. He went on to do his PhD at the University at the California Institute of Technology. And following a postdoc there and at the Max Planck Institute for Quantum Optics, he started as an assistant professor in Lincoln, Nebraska. And he's been there since. Martin was just elected a fellow of the American Physical Society last year for much of the work that he's going to tell us about. It's a great pleasure to have you here, and I'm looking forward to your talk very much. Take it away.
Thank you, Tom, and thanks to all the organizers for inviting me. Okay, let me get this going. The screen show okay? Okay.
Yeah, looks good.
Right. Okay. So as Tom said, I'll be talking about ultrafast imaging with electron diffraction, and let me just motivate a little bit what is sort of the general direction of our research. And what we're interested in is to investigate or to understand energy conversion at the level of single molecules, and specifically light getting converted into chemical energy, basically on changes in the structure of the molecules, or into mechanical energy or heat, basically energy dissipation. So I have here, so there are actually many examples of molecular reactions that where light gets converted either into converts the molecule into a different structure, induces vibrations, which then dissipate the energy. And you can see this in biological systems. This is one example of basically the first step in the fission process, where retinal goes from the cis to the trans conformation. This changes the chemical properties and triggers a whole bunch of other events that then result in you seeing something. Another example is, for example, this molecule where you can transform from this structure to this other one by absorbing a photon. And here, this structure is highly strained, so it actually stores energy in the conformation. So this is a candidate for example, for molecular energy storage. And another example is if you look at DNA bases, they basically they absorb light and they very quickly relax and convert this energy into vibrations. And the current understanding is that this very fast conversion into vibrations actually reduces the rate of damaging chemical reactions in your DNA. Now, all of these reactions have something in common, is that they take place on very fast timescales, and many of these reactions are also very efficient. And these two things are coupled together, because if you want to do something very efficiently, if you can do it very fast on femtosecond timescales, then you're faster than the timescales for energy dissipation. So you can drive this energy into a specific path in the sort of if you want to think in the potential energy landscape. So the goal is really to understand how these things take place, and basically at some point be able to control this reaction, or maybe design molecules that will do exactly as you want. And the issue here is that there's really many degrees of freedom. So it's you cannot simulate these things and keep track of everything that is happening. So there really has to be a lot of interaction between experiment and theory to move these things forward. And one important point is that if you want to understand what happens, you need to see in what electronic state you are at all times, and you also want to see what the structure is doing. And spectroscopic methods, laser-based methods, are really good at capturing changes in electronic states. And diffraction methods are sensitive to the motion of the nuclei. But it's only very recently that diffraction methods have reached the temporal resolution to be able to see these reactions as they take place. So you really need to be on a time scales of hundreds of femtoseconds or less to actually see the coherent motions that take place. So to actually see the transformations as they happen. So I'll split my talk in three parts today. First, I'll give an introduction of ultrafast electron diffraction. So just so everyone is in the same page of what it is and what information you can get. Then I'm going to talk about two specific reactions that we investigated. One is a proof of principle experiment, and then moving to more complex reactions and see how much we can learn. And then at the end, I'll go back to a simpler case of rotational motion and hopefully show you what we believe is actually a molecular movie rather than just images. So from diffraction to structure. So if you want to see something, you basically, or make an image or a diffraction, you need to use waves, and the resolution, or basically the limit of what you can see, is determined by the wavelength of your radiation. And here electrons have a big advantage in that it's very easy to make kilovolt electrons which have picometer wavelengths. That's why electron microscopes are so successful. Now, the basic idea of what we do in diffraction is, imagine you have, this is the famous double slit experiment. So I have a wave coming in, two slits, and then I record a diffraction pattern here. And the period, so the distance between the maxima and this interference pattern depends on the distance between these two slits. So now imagine I do the same, but I replace the slit by a diatomic molecule. Now, instead of getting diffraction through the slits, I get diffraction from each of these two atoms, and I measure the interference pattern. Now, if I measure this interference pattern and I know the wavelength and the distance, I can calculate what this distance is. And the trick here is just you pick the wavelength and the distance such that your interference pattern is microscopic, so maybe a period of millimeters. And now you make a microscopic measurement and you know a microscopic distance. So I measure something in millimeters and I can determine this distance on sub-angstroms. So the trick of diffraction is really this: convert the distance into a sinusoidal interference pattern that you can more easily measure. Now, when we work with molecules, we typically have a gas of molecules, and we put as many molecules as we can into the interaction volume because the it's a gas, so it's still a weak scatterer. And so we have, for example, a gas jet, and we intersect this with an electron beam and record the scattering pattern. And because this is a gas of molecules, molecules are randomly oriented. So instead of like a bar interference that you would get rings. And you do lose information because of the random orientation of molecules, but you can still recover basically the distance between the atoms in the molecule. So you have one-dimensional information. And I should mention that this method of gas electron diffraction has been a tool for structural chemistry for a long time. The first experiment with gases was in 1930, very shortly after the demonstration of the wave properties of electrons. And since then, there are a lot of experiments with gas phase molecules. So what is the signal that we measure? So we do everything in terms of momentum transfer here, S. So for small angles which we deal with, this is basically just right? It's 2 pi theta over lambda. So it's a scale of the scattering angle. And there are two components. This is atomic scattering intensity, which is basically the signal that you would get if you did not have any interferences. And then we have this molecular scattering, which is a small modulation on top of this. And again, this is because of the random orientation that reduces the modulation of your scattering. And the signal that we get looks like this. So it's a sum of sinusoidal terms. So here Rij is the distance between atoms I and J. So for each pair of atoms in the molecule that I can make, I get a sinusoidal pattern. So then, for example, for this molecule, so what we do is we rescale this scattering just because of the decreasing scattering amplitudes with angle. And then we can get an interference pattern that looks something like this. It's circularly symmetric because of the random orientation of the molecules. And so we can do an azimuthal average and get something like this. And again, this pattern is the sum of some sinusoidal functions. So we can analyze this by a Fourier transform or a sine transform. And we get now a pair distribution function. So our pair distribution function would have a peak corresponding to each interatomic distance in the molecule, and not just the bonded distances, but we are just sensitive to position. So all of the possible distance will be reflected here. So for example, in this molecule, the longest distance is the distance between the two iodine atoms. So these are two iodines, carbons in black and fluorines in green. So the longest distance is 5 angstroms, and this is what you see here. So there's a peak corresponding to this distance. And then here you see 3 other peaks. And of course, there are more than 3 distances here. But what happens is because of the limited resolution and because we are projecting all this information into a one-dimensional pair distribution function, some of these overlap. So some distances can be detected in isolation, but in other cases they overlap, and we have to deal with this. Okay, so this is all for static diffraction, but what we want to see is the dynamics. So what we do is now we have the same setup, but we introduce a laser beam. So we use a laser pulse, first excite the molecules, then probe them with an electron pulse and record a scattering pattern. Then we vary the delay between laser and electrons and do this many, many times. You will see that a lot of our scattering patterns have a region in the center with no data. And this is basically because there's a directly transmitted electron beam, which is much brighter than the scattered part. So we have to plot this in general. Now, because these signals are small and there's a lot of background scattering, we almost always work in differences. So we take a pattern, let's say with laser, without laser, and then we create the difference. And with this, we create a difference pair distribution function. So for example, if you break a bond in the molecule and dissociate or remove one of the atoms, you see this negative peaks, and this tells you which distances are now missing in your molecule. And if you create new distances, then you will see new positive peaks that appear. And this usually works quite well. And one of the reasons is that the ground state structures are usually known very accurately. And if not, we can determine them pretty accurately just by doing diffraction measurements. A lot of this technology, so a lot of this, the data analysis mechanism and a lot of the early technology was developed in the group of Ahmed Suwail. So he got the Nobel Prize for femtochemistry, right? Basically bringing femtosecond lasers to do chemistry experiments. And then actually he moved and did a lot of electron diffraction experiments. And he was able to push the resolution all the way to the regime of a few picoseconds and investigate the reaction kinetics and determine the structure of transient states. And but couldn't quite get to the resolution of femtoseconds, which is what you really need to see the coherent dynamics. And in a minute, I'll tell you why. We started working on this in my group a bit more than 10 years ago. And I won't go into detail with this, but if anybody wants to talk about this later, I'd be happy to. So one of the first things we did is to see if we can actually extract more than one-dimensional information from the diffraction patterns by aligning the molecules with a laser and then doing diffraction. And the answer is yes, you can extract more information. It's not very easy, but it's doable. But you see, this is about 10 years after Sewell's experiments, and we managed to push the time resolution to below a picosecond, which is what we needed, but we're still not at this sort of 100 or 200 femtoseconds that is needed. Now, why is this so hard to do? So one reason is just the Coulomb forces. Electrons repel each other, so you make a very short pulse of electrons, and then after it propagates for a short distance, it actually becomes broader again. And even if you make a pulse with just maybe a few thousand electrons, which is not much charge, this is a significant problem. The second problem is that these experiments were typically at 20 to 30 kilo electron volts of electron energy. And then the speed of the electrons is 1/4 or 1/3 of the speed of light. So as you go to your sample, which may be a gas beam or a gas jet, the laser and the electron pulses have different speeds. So the time delay between the two is not constant as you go. And this is enough to blur the resolution by a picosecond in just a few hundred microns of sample. So one way to minimize these two problems is to go to higher electron energies. You go to relativistic electrons, and then the space charge effect is reduced significantly, proportional to gamma cubed approximately. And the velocity mismatches can become insignificant. And with this, you can reach a resolution of about 100 femtoseconds. It introduces some other difficulties, but it's really transformational in that now you can be in the regime where you can actually see the coherent nuclear motions. So for this, we collaborated with the team at SLAC, led by Xiji Wang, and Ji Yang was one of the leaders in setting this up. And so this is what it looks like. So this is the electron gun. So now you use it uses RF fields to accelerate electrons to between 3 and 5 MeVs. Then there's some electron optics and diagnostics. This is the sample chamber. So the distance from the source to the chamber is less than a meter. And now the wavelength of these electrons is very small. So the diffraction angles are very small. So you actually have to put your detector far away, about 3 meters away. This was my main worry going into this about the small diffraction angles, but the beam quality is also very high. So it turns out that it works. And this is just it's an old picture, but this is what the setup used to look like a few years ago. It was shared, it's in a bunker, which was shared with another experiment. That's why we were only allowed to go under the table. But anyway, here's the setup. And with this, we're able to reach resolutions below 150 femtoseconds and basically operating at 3.7 MeV. The wavelength is 0.3 picometers, the wavelength of the electrons. So we did 2 proof of principle experiments just to show how this all works, and I'll tell you about one of them. So in this case, because the velocities are matched, you want to have a collinear propagation of the electrons and the laser through the sample. So we use these Holy mirrors to get the laser in and out of the chamber. And in this case, there's actually a hole in the screen for the through beam to pass through. You know, these MEV beams, if you stop them, they make a lot of X-rays. So that beam actually goes through. And then the experiment that we did was the following. We take iodine and we excite it with a green laser pulse, 40 femtosecond laser pulse into a bound state where basically now the minimum of the bond length is now displaced with respect to the ground state. So we excite vertically here, and now this creates a vibrational wave packet. So we basically undergo this motion up in the excited state, and this is what we want to see. This is a simulation of this vibrational wave packet. So the equilibrium distance in the ground state is about 2.7 angstroms. And then once you go into the excited state, you go into the vibration up to about 3.9 angstroms and then back. And the period is about 400 femtoseconds. So basically what we want to see is as this bond length is changing, as the distance between the two atoms changes, then we should see changes in the diffraction pattern. So the first thing I show you here, so this is a difference diffraction patterns average over basically one period of the vibrational motion. So the fact that you see anything here means that the bond distance is changing. And I can also point out here that the diffraction is no longer isotropic, so the circular symmetry is broken. And this is because the excitation probability depends on the relative angle between the molecule and the laser polarization. So you are selectively exciting molecules along a certain orientation. So the excited molecules are actually aligned along the direction of the laser polarization. Now, in this case, because this molecule is simple, so this is what we measure, basically the change in the diffraction signal, but we know what the ground state looks like, so we can actually extract the interference term corresponding only to the excited state. And this is what it looks like here in experiment and simulation. So you start with an interference pattern of a certain period, then you come in with a laser, and you see that this period changes rapidly. You also see it here. And then you can see that there are some oscillations also going on at later times. From this diffraction pattern, we can, through a Fourier analysis, we can extract the pair distribution function. Here, there's only one distance. So again, what you see here, this is time going down and bond length increasing to the right. So we start here, we come in with the laser, and you see this goes up and down and then up again, and it matches the theory quite well. And I should add here that this diffraction measurement is sensitive to the distance between the two atoms, right? So here we extract the distance versus time, and you see there's a reasonable match between theory and experiment. But also this method is also sensitive to the shape of the wave packet. So we're also sensitive to dispersion of the wave packet. In this case, a lot of this broadening that you see is caused just by the time resolution, basically smoothing in time because of time resolution. But there is already some contribution just from the dispersion of this nuclear wave packet. And I just want to mention that Ji Yang here, he was in my group, and then he moved to Slack, and he was basically the driving force behind this experiment. So after doing this demonstration, then this gave us some confidence that we could start to look into more complex reactions. But before I move on, I think maybe this is a good spot for questions, if there are any.
Yeah, that's perfect. There are several questions here, and maybe I'll start with the clarification one. So Adam Kaufman asks, I might have missed it, but why doesn't the orientation averaging smear out the signal for a gas phase measurement?
Oh, that's a good question. It's actually not so easy to explain. If you do the integrals, you can see it, but the one way to explain is maybe imagine if you have a diatomic, that the distance actually would make a sphere, right? So it makes a sphere. So if you think about this, if you project this sphere, you don't get nothing, you still get something. So it's basically a three-dimensional shell, right? So the distance in a diatomic would make a shell, and then you project this shell into 2 dimensions by the diffraction, and you don't lose all the information. You get basically get a circle. That's
Okay,
the
great.
that's the best I can do without going into the math.
Okay, great. So then we also have another question here about what do you mean that the energy conversion happens through atomic motion? Does it mean that all of the fast energy conversion mechanisms are vibrational?
Um, no, well, so you start in the electronic excited state, right? And then you move to the ground state, but there's some there's a lot of energy that you deposited into the molecules. So eventually all this energy has to go either if the molecule is isolated, it has to go into breaking bonds or making new bonds or vibrational energy. Or I guess you can have also, if you break the molecule, you can have rotations. But yeah, eventually all this energy has to find its way to vibrations.
Okay, great, thanks. And then I'll sort of combine two of the remaining questions. So which were really about sort of the limits that the method has, what type of molecules can be probed, for instance, the mass of the atoms or the molecules, what they are made of, how tight are the bonds, and then I guess sort of as part of this, I'll merge in and how would this work for condensed phase?
Okay, so uh, the kinds of molecules that can be probed. So this is sort of a fast evolving uh, field. So we started with very small molecules. We're now moving to larger molecules, and so we started, for example, with molecules with heavy atoms that scatter a lot, but we have also now done molecules which do not have, so basically just carbons and hydrogens, which do not have any high scattering elements, and that also works. And I think maybe we are at the level of 10 to 15 atoms in a molecule. And, it's just an issue of signal to noise at this point. Uh, how much signal you can get, and the larger the scattering angles that you can get, the better the resolution you can have. And I think in many cases, you can see changes in the bond lengths at the order of a few percent. And the last part of the question was, oh, I can't hear you. I think you're
Yeah, I
muted.
was muted, sorry. So the last part of the question, or the last question, is that are the dynamics modified when the molecules are in the condensed phase, and what kind of relevance would that have for energy storage?
Oh, yes, but very likely the dynamics are modified in the condensed phase. So the value of doing experiments in the gas phase is that you can hope to understand sort of the intrinsic response of the molecule. And then if you put it in solution, then what it does would probably be different through the interaction with the solvent. And if you change the solvent, then it would probably change again. So I think ideally we want to understand sort of what the molecule does on its own, and then it would be interesting to compare, what it does with what it does in solution. And I have to say we are also working on that at Slack. There's been some first demonstrations of experiments in solutions, but uh, eventually we want to use the experiments to develop more predictive theories so that we can understand what happens in the gas phase, compare that with theory, and maybe then be able to predict what would happen if you put this molecule with this solvent or that solvent.
Okay, great, thanks. So I think then that's a good place to sort of continue on, and we'll get to the remaining questions at the end.
Okay, all right. Okay, so let's now move to this other reaction. So this is a reaction that the group of Wales studied, first with using mass spectroscopy, and then also with diffraction. And it's a halogen elimination reaction. And it's very interesting because you start with this molecule. Again, you have 2 carbons, 2 iodines, and 4 fluorine atoms here. you excite it with one UV photon, and first one of the carbon iodine bonds will break, and after a long delay of tens of picoseconds, then you get the other carbon iodine bond breaking, and you make C2F4. Now, in this first part, there are two possible conformers that have very similar energies that you could, in principle, make. And so Sewell used ultrafast electron diffraction, and he determined that only this conformer actually gets made. Now, interestingly, there was a experiment not too long afterwards of a similar molecule in solution. This is with hydrogens instead of fluorines. And in solution, they saw that you make this actually bridge. So they call this the bridge structure, and this is a classical structure here because this iodine is bonded to the two carbon atoms. And so this raised some questions whether this structure could not also exist in the gas phase, but just on shorter time scales than basically the 5 picosecond time resolution of this experiment. Because once you're in solution, if you make this structure, you could very quickly dissipate energy, and maybe this is what makes this structure stay. So we thought it would be interesting to further investigate this reaction. And the first question is just whether to determine if this bridge structure actually exists on shorter times, and then it just decays into C2F4 or into this other structure. But there are also other questions that we wanted to address. Just as a demonstration, can we actually see how the bond breaking event leading to this formation? And one thing that we also thought would be very interesting to investigate is after the bond breaks, we know that there's we're creating coherence when we go to the excited state, but after the bond breaks, does this coherence survive in coherent vibrations of this structure, or is all this coherence lost and dissipated into basically thermal vibrations? So what I have here is a simulation from the group of Todd Martinez of this reaction. So this is right after the bond breaking event, the simulation starts, and the runtime is about a picosecond. And this is now, these simulations, in order to interpret them, you basically run this maybe 100 times from 100 different initial states, and then you look at sort of the average of this to try to understand what the molecule is doing. This is one representative trajectory, and you can see that it does not make this bridge state, and of course there's lots of vibrations. Now the question is, will these vibrations show up as coherent vibrations in the experiment? And also, can we confirm with the experiment that this bridge structure never actually forms? So you see the iodine moves towards the center position, but it never actually gets bonded. So let me show you first the data. So this is the experiment. Now I'm showing you the changes in the pair distribution function. So here we have distance going down and time going from left to right. So the zero level here is on the orange. So the green and the blue lines, so these are negative. So basically you remove one of the iodine atoms. So all of the distances containing iodines are now missing. This peak, for example, contains two distances, but one of them is missing. So you lose some of it, and you lose this distance, and you lose, this is the longest, the 5 angstrom distance between the two iodine atoms, and it's missing. And you see the corresponding negative, depletion regions in the theory. Okay, so that's the origin of this negative regions. Now there's also some positive regions of this red region. So here, for example, in the theory, you see these very fast oscillations at short distances, right? So this is vibrations in the carbon fluorine bond that are not resolved in the experiment because of the limited time resolution. The other sort of obvious features that are these streaks. So these are new distances moving very fast, right? So the distance is increasing very fast. And this is the wave packet of the dissociating iodine atom. So you break the bond, and this atom moves away very, very fast. And we don't quite see this in the experiment, and the reason is, again, the time resolution of the experiment. So here you see this is the theory, and if we convolve the theory with the time resolution of the experiment, you see that these very nice streaks become this sort of blob. So you have two red blobs here that also show up in the experiment. So this positive region, so this is for the dissociated wave packet, but there isn't quite enough resolution in the experiment, for example, to see the streaks that you would need to get, for example, the speed of the two atoms. Now, there are other features in here. So, for example, you see there's a modulation here in the amplitude where there was nothing, now there's something. And it does not show very clearly on these pictures, but there's a modulation also in the amplitude of this blue peaks. And so this is dissociation, right? This is the signal from dissociation. So let's look at this now, these modulations in here. And so we look, let's say we look at two specific distances. Now imagine if we had only one distance in the molecule, like a diatomic, and if it was vibrating coherently, you basically see the probability increase in one say end of the motion and decrease in the other one. So you would see periodic increases and decreases in the amplitude of the signal. Now we have many distances here, so it's a little bit more complicated. But the fact that you see these modulations in the amplitude of the signal are strongly suggestive of coherent motions. And in fact, we see that there's pretty reasonable agreement between the simulations and the experiment here. So what we do now is we basically look at the region after 200 femtoseconds. So we want to basically remove the contribution from the dissociating wave packet, which is this very bright signal here. Again, it's brighter in the theory because of this convolution with time in the experiment. So if we look at these oscillations now in more detail, so here, for example, the red corresponds to 3.9 angstroms and the black corresponds to 3.1 angstrom. So you see at the shorter distance, there seems to be an oscillation, but then it sort of defaces very quickly. While at 3.9 angstrom, there's an oscillation which is almost right on top of the simulation, and it seems to persist at least for 800 femtoseconds here. So we can try to understand this a little bit more by identifying what, so these distances that we're looking at, what do they actually correspond to in the molecules? So this corresponds to the carbon iodine distances. So there's a short one and there's a long one. And then the fluorine iodine distance is basically just one. So if we now see where these two distances, 3.1 and 3.9 angstrom, line up, in the carbon iodine distances, so this is basically the vibrations extracted from the theory, and that this is where we are looking in the experiment. So the black line, the shorter distance, has some contribution from the carbon iodine distance and the fluorine iodine distance. While with the longer distance, we're basically only probing the oscillations in the fluorine iodine distance. So this red curve corresponds only to that oscillation, and it's basically this motion in the molecule. So this iodine getting closer to the and farther away from the fluorine atoms. And so it could be that this defacing is faster defacing in the experiment is due to looking at more than one distances and somehow they go out of phase. But to tell the truth, we're not exactly sure why one of these lived for longer than the other one. Okay, and the final piece of this puzzle is basically to determine whether we really have this, whether this bridge structure forms at all or not. Now, the advantage that we have is that we can look at a very short time. So we look at 200 femtoseconds after the excitation, and we see already that the pair distribution function agrees quite well with this classical structure and really does not agree with this bridge structure. Now 200 femtoseconds is roughly one vibrational period of the CI bond. So you couldn't really make any structures any faster than that. So if it's not there by 200 femtoseconds, then it means it's actually never formed. Now, I should clarify that with this analysis, we don't mean that this is exactly what the molecule looks like, because we know that it has large amplitudes of vibration, and what we're measuring is includes some averaging over those motions. But what we can say is that the structure that exists is much closer to this classical structure than to this bridge structure. So in combination with the theory, I think it's pretty conclusive that this structure actually never forms, the bridge structure. And I'd like to point out Kyle Wilkin, who did a lot of the experimental work and most of the data analysis for this. So summarize. So we have determined that this bridge structure never formed, which was an open question from before, and we also seen that at least some coherent motions survived this bond breaking effect, which on molecular scales, this is quite a violent event, but still there are some coherence that survives in the vibrations after the bond breaking. Okay, before I move to the last part, maybe if there are any questions, I can take some questions now.
Great. Okay, we do have a couple of questions here. So the first one is from Chi-Dong Lin, and who asks, how do you distinguish the width of the radial distribution, or how do you distinguish that the width is from the radial distribution from vibrational wave packet or from a limited range of a Fourier transform?
How do I distinguish? I mean, in this oscillations, or I'm not. If
I think the question is in general, like how do you know whether the width that you might see of your pair distribution function comes from the intrinsic width of the wave packet?
Oh, okay.
That comes from a limited range of momentum transfer or other issues associated with the Fourier transform of your S-independent data.
Yeah, no, I get it. So we can calibrate just from the static diffraction quite accurately what's the width in the pair distribution function, and then that gives us a good idea of what we can observe and what we cannot. So these widths are typically 0.6 angstroms or 0.7 angstroms. So if you have a wedge packet which disperses by 0.1 angstrom, you won't see it. But if it becomes 0.5 angstroms wide, then you have a good chance to detect that.
Okay, great. Thank you. I think there's one more question in this section, but I'm going to sort of opt to just leave it for the end because it's a little bit more of a general question.
Okay.
And this way we can let you go through to the end and allow more time for questions then.
Okay, thanks. Okay, and yeah, and then I just wanted to advertise a little bit for anybody who's interested that, this Slack setup has now become a user facility. So there was a first run of 20 experiments that just finished a couple of months ago. There's probably going to be another run next year. So anybody who's interested, you can go and don't have to you don't have to build this in your lab. You can just go and do the experiments there. And this is just a list of the publications that have come from the setup in the last few years. And the blue ones are the ones that I talked about. Okay, so I want to go back to the idea of a movie because I haven't shown you any movies. I showed you one, but it was a simulation. I haven't not shown you any movies from an experiment. So what do we still need to do to actually make movies? So one thing would be that we would need to retrieve the 3D structure from experimental diffraction patterns. So this, we don't know how to do this, but we are working on it, and hopefully we'll have something soon. And also that we just need, we need more signals, right, to take more frames so that we can actually build a movie. So you need a time resolution, right, which is comparable to what you want to see, but you also need to take more frames so you can actually make a movie. So this we've been working at in my lab in Nebraska, and we found a solution. And part of the solution is that this kilovolt setups can usually run at higher repetition rates than the MEV setups, so you just get more signal just because of that. But we still have to solve these two issues of the space charge effect and the velocity mismatch. So for the space charge effect, we use a buncher cavity, which can recompress electron pulses. So this is technology borrowed from accelerator physicists. They've been doing this for a long time. And the second is that we can use tilted laser pulses to match the velocity of the electrons. So basically manipulating the laser intensity fronts with optics. So the first idea, which is to recompress the electron pulses, is in principle quite straightforward. So you generate an electron pulse by a laser on a photocathode, put a lot of charge in it, let it spread out, and then you have this cavity which has a longitudinal electric field. So if you look in here, when the electron pulse enters into the cavity, you have fast electrons in front, slow electrons in the back, just from the dispersion. And then you have a force which slows down the electrons. As the electrons go through the cavity, the field changes direction. So now you accelerate the electrons in the back. So coming out, you have now slow electrons in the front and you have fast electrons in the back. So the bunch will just compress at the predetermined distance from the cavity, and that's where you put your sample. So this cavity acts basically like a temporal lens. And this was proposed in 2007 and demonstrated a few years later. The trick here is how to synchronize this field with the electron pulses. So this setup was basically built by these three students which worked on different parts of the setup. And don't worry, I won't go to all the stuff here, but just to show you the quickly in red, this is the laser path, and we use a grating to tilt the laser pulse, which then comes into the chamber at the right angle. And then in here, so the laser is going in this direction, but the intensity front is parallel basically to that of the electrons. And in this way, you can match the longitudinal velocity of the electrons to the velocity of the laser in the same direction. And the end result is that as they go to the sample, the time delay between the laser and the electrons is fixed. So you don't get this blurring due to velocity mismatch. And now the same laser is used to trigger the electron gun after converting it to the third harmonic. And so the green here is the path of the electrons, some electron optics. Then it overlaps with the gas and with the laser here on the target chamber. And then we detect the scattering here. And all of this path in purple, this is basically the electronics to drive this RF cavity and to synchronize it with the laser. And again, you have to synchronize on femtosecond timescale. So this is what basically was most difficult for us. So compared to our first generation setup, with this setup, we can increase the beam current by a factor of 20 because we can recompress, we can put more electrons in there, improve the temporal resolution to 250 femtoseconds, and the timing stability, which is of course very important for doing experiments, is about 50 femtoseconds over several hours, which is comparable to the setup at SLAC. So let me just show you what this actually looks like in the lab. So I'm showing you just the electron part here. So this is the electron accelerator. So it's a DC accelerator, and it's triggered by a laser pulse. This is UV, but I just drew it in red here. And then there's some electron optics, and this is the path for the electrons. This is the target chamber. So there's a window for the laser also. I did not draw this path, but there's a laser that comes in to this window. Gas comes in from the top, and they all overlap in here. Now, after you trigger the electrons, you make a short pulse, which gets accelerated, then this spreads, then it goes to this buncher cavity where you reverse the velocity distribution, and then if you do everything right, you have a compressed pulse right on the sample here in the target chamber, and then you collect the scattering here on the detector. And of course, the laser and the electronics parts are not shown here. So again, we thought of, what's the first experiment that we can do that would be interesting and show that all of this actually works. So we thought about alignment. So the idea here is to do impulsive alignment of molecules with a short laser pulse. So here you have a distribution of randomly oriented molecules, and then you hit them with the laser, and then after the laser pulse, they will be aligned. So as you see, they're not oriented, they're aligned, so some point up, some point down. And now if we look at the changes in the diffraction pattern, so the structure is not changing. So however, we would see something if we change the orientation of the molecules. So if the molecules are aligned, then the diffraction pattern becomes anisotropic, and you can see this. So here at the bottom, you have the time delay between lasers and electrons. And so here we're advancing the time delay. So this is right before time zero. This is right after time zero. So 300 femtoseconds after the laser excitation, we're probing the electrons, and you can see a little bit of anisotropy building up. But actually, the peak of the alignment happens at a longer time after the excitation, and then you can actually pretty clearly see this alignment. And then after a little while, it goes away. So you can do something like map the anisotropy in the diffraction pattern versus time. Oh, hold on. Oh, here we are. So here's where the laser comes, and here's the peak of the anisotropy, which corresponds to the peak of the alignment. And then the alignment goes down, but you see it doesn't quite go down to zero. And we can follow this on a longer time scale. So now I switch molecules. We did this experiment with nitrogen. And you see here's where the laser comes, and you first see some alignment, then it dephases, but the coherence is not lost. So you see all these periodic revivals where you get alignment, which means a sort of a prolate distribution, and you get anti-alignment, which is an oblate distribution. And when you get to this half revival, you basically retrieve the same degree of alignment as at the beginning, and you see these very fast changes and so on. So from this, we're able to determine actually what our time resolution is, in part because this can be simulated very accurately. As you see here, the red line is the simulation. But now we have all these diffraction patterns of aligned molecules, and it turns out that you can actually, well, you remember from the diffraction pattern, you can get the pair distribution function, which means from the anisotropy, you can also get the angular distribution of the molecules. So from this, we're able to get basically the probability density of this rotational wave packet at different times around the alignment. So what you see here, you can think of this as you have a 3D distribution, and then you make a slice through the center, and this is what we're looking at. So okay, I don't have a picture, but if you had random orientation, this would just look like a circle with uniform intensity. When you have a prolate distribution, it looks like this. When you have an oblate distribution, it looks like that. And you see it matches the theory quite well. And the reason it doesn't match exactly, again, is the time resolution of the experiment. So there's a little bit of blurring of these structures. Okay, so the last thing I want to show you is the movie that we made, and one of my students, Yan Wei, was the one who did all the data analysis to create this movie. So let me just play it. So again, this is the basically the probability density of the rotational. No. Probability density of the rotational wave packet. So here it goes. So it goes quite fast. So the frame rate here, if you want to think of this as a movie, is 10 to the 13 frames per second. So let me slow it down. So we start here with the prolate, with the maximum of the alignment, right? And then it goes back to almost isotropic, but not quite. And then you get all these small revivals. And then when you get to about 3.8 picoseconds, like this revival, you get the maximum alignment, and then very quickly, within 300 or 400 femtoseconds, it goes to the anti-alignment and then back, and again, all these different revivals. And so with that, I'd like to acknowledge all the members of my group who did all the work, and also our collaborators in the SLAC MEV UED team at Stanford and Potsdam University, and particularly Marcus Kerr and Thomas Wolf, and this is the SLAC UED team. And also to our theory collaborators, Seng Lee, and everybody in the group of Todd Martinez. And thank you all for your attention also.
All right, great. Thank you very much for a beautiful talk, Martin. There are a few more questions that we'll trouble you with. So one question is, you indicated at the beginning of your talk that this is sort of a counterpoint to spectroscopy measurements, which sort of probe, electronic energies or something. And here you're directly looking at structure. So optical pulses are not amenable to that because you just aren't able to resolve the structure. But X-ray photons would have the sufficiently short wavelength. How would you compare, just roughly the X-ray diffraction measurements of the same dynamics to the UED ones?
Okay, that's a very interesting question. So to zeroth order, you can get the same information from X-ray diffraction and electron diffraction, provided you have the same wavelength or you measure the same range of momentum transfer. So that's basically, I didn't go into this, but we're sort of implying the independent atom model, where all your signal comes just from the nuclei, and the bonding electrons don't do anything. But we've had already several examples where we have to go beyond this model actually to really interpret the data that we have. And once you go beyond the independent atom model, then X-ray and electron diffraction actually give different information, because X-rays basically scatter only from the electrons in the molecule, and electrons scatter from the potential or from the total charge density. So you get signal contributions from nuclei and electrons. So in this case, you get different information from both. So if you have only a proton which is moving without and the electron is maybe doing something else, then you get very different signals in X-rays and electrons. And also the inelastic part of the scattering is different between X-rays and electrons. And we're also starting to learn a little bit how to get information from the inelastic scattering.
Okay, great, thank you. And then another question from Nick Rutzler would be, how long are the rotational coherences persisting on their own?
Probably a very long time, much longer than we can probe, because these molecules are not there. The gas is not very dense, so the rate of collisions is very slow. So I don't know what the actual number would be, but I assume very, very long.
I mean, I guess there's a difference in the sort of dephasing and the loss of coherence, I guess, too, right?
Yeah, so it's constantly dephasing and rephasing, right, which creates these revivals. But the coherence should last until basically it has to until the molecule interacts with something.
Okay, and then perhaps one final question is the extent to which you see the measurements sort of like, you talked about making a movie and you distinguish between a simulation movie and sort of an experimental movie. to what extent do you see the measurements as sort of verifying things that can be calculated, and to what extent do you see them as making measurements that are not of calculable entities? So, you know, if I were sort of maybe an electronic structure person or somebody that does quantum dynamics, maybe I would say, oh, well, you can calculate things at such a high level. What do we need experimentalists for? So how would you sort of maintain your job security?
I guess well, you can quickly realize that you cannot do these calculations exactly because there are so many degrees of freedom. So that's the first order answer. Of course, you know, I think we're all experimentalists in theories striving towards, you know, making better models, right? Which means better theories. So maybe eventually it would drive experimentalists out of a job, but I think that's probably far into the future. And also, you know, experiments are getting more and more precise, so they can push the theories more and more, right? So if an experiment only extracts one time constant, right, then maybe any theory can match that one time constant. But now if we can see specific motions or specific vibrations corresponding to specific modes in the molecule with times, right, and spatial information, that's a much more stringent test for a theory.
Okay, great. So I'm gonna, well, thanks again, Martin. I think that sort of brings us to the conclusion of the 1 hour. And I'm gonna quickly ask you if I can share my screen and then just show an advertisement for next week. And then invite everybody to join you in the post-Vamos discussion. And I think the link has been sent out in the chat here. So once I share my screen, then you can click on that link to find yourself in the chat, in the discussion room. So let me go ahead and pull up the slide that I wanted to show here. Okay, so next week's talk will be given by Benjamin Lev from Stanford University. He'll be talking about topological pumping of a 1D dipolar gas into strongly correlated pre-thermal states. And the QSS seminar next week will be given by Eric Hudson from UCLA, talking about laser spectroscopy of a nucleus. Okay, and anything else?